Okay, so let's jump into this. Using a mirror to actually silence something, quantum noise no less, that feels, well, wrong?
It definitely sounds counterintuitive,
Does
doesn't it?
it?
But yeah, that's essentially what researchers over at Swansea University have figured out with tiny particles.
Right. So this deep dive is about unpacking that, how this mirror setup actually works, this magic.
Exactly. We're looking at how they managed to reduce this quantum noise.
Okay, maybe step back a second. Quantum noise. What's the core problem here that needs mirror magic?
Well, think about trying to measure something really, really small, like a nanoparticle. To see it, you need light, right?
Right.
Photons.
Uh-huh.
But even a single photon carries momentum. So when it hits the nanoparticle, it gives it a little nudge, a kick.
Ah, so the act of looking actually disturbs it.
Precisely. That's what we call quantum backaction. It's, a fundamental limit. Your measurement inherently changes the system you're trying to measure.
It's like trying to find out exactly where a balloon is by, I don't know, throwing ping pong balls at it. You find it, but you also knock it away.
That's a great way to put it, yeah. And what these researchers discovered is, if you put this particle right in the sweet spot, the exact center of a specific type of mirror, a hemispherical one, things change.
Hemispherical, like half a ball. Why that shape?
Good question. That precise geometry, with the particle perfectly centered, does something amazing to the scattered light. It makes the particle effectively identical to its own reflection.
Identical to its reflection, so the light can't tell them apart.
Exactly.
Yeah.
You essentially lose the ability to pinpoint the particle's position from that scattered light. And here's the really wild part. One of the researchers, Rafał Gajowski, basically said their work showed that if you create a situation where you can't make the measurement, the disturbance itself, it just disappears too.
Hold on. You make it impossible to measure accurately, and that makes the quantum noise go away, not like less light or something.
Right. It's totally the opposite of what you might guess.
Yeah.
And this noise reduction happens exactly when the light scattering is strongest.
Strongest scattering, but less disturbance.
Yeah. Dr. James Bateman highlighted that. He said, what's particularly surprising is that the backaction disappears precisely when light scattering is maximized. It flies in the face of intuition.
So it reveals something fundamental about
What here?
information and disturbance being linked.
That's the core idea. If the setup prevents you from extracting the position information, the back action associated with getting that information just vanishes. It's like the universe says, okay, you can't know, so I won't disturb it.
Wow. Okay, so this isn't just a neat physics trick, right? What can you actually, do with this?
Oh, the potential applications are really exciting. For starters, it could let us create proper quantum states, superposition, entanglement with objects much bigger than atoms. I think nanoparticles behaving quantumly.
Seriously, getting nanoscopic objects into quantum states, that's big.
What else? Well, it opens the door to testing quantum physics itself at scales we haven't reached before. Maybe even probe that really fuzzy boundary between quantum mechanics and gravity.
The quantum gravity link, the holy grail for physicists.
Sort of, yeah. And there are ambitious projects, like the proposed MAQRO space mission, that aims to test quantum mechanics with large objects in space. This kind of technique could be crucial.
And sensors. You mentioned sensors.
Definitely. Imagine developing incredibly sensitive sensors based on this, detecting tiny, tiny forces, maybe gravitational waves, maybe subtle biological interactions. Possibilities are huge.
So this fits into that whole field of levitated optomechanics.
Exactly. That's where scientists use lasers to trap and control tiny particles, levitating them. People have already cooled these nanoparticles down to their quantum ground state, the lowest possible energy level. This mirror technique is another step in gaining really fine control.
Okay, so let me try and recap. You put a particle in the perfect spot inside this half-sphere mirror. It becomes indistinguishable from its reflection. Because you can't precisely measure its position anymore from the scattered light, the quantum backaction, the disturbance from measuring, just disappears.
You've got it. It happens precisely because the measurement becomes impossible under those conditions. We're manipulating the information we can access, and that directly quiets the quantum world.
It's incredible. Real control over the quantum fuzziness by controlling the measurement itself.
It really pushes the boundaries, and it opens up so many avenues for fundamental science and, down the line, maybe some powerful new quantum technologies.
It really makes you think, doesn't it? If we can negate quantum noise by cleverly blocking the measurement, what other fundamental limits might just be waiting for us to find the right way to not look? Something to ponder.